Hi, we are the Mask Crusaders, and our project is about detecting that face masks are worn correctly. I'm David. I'm here presenting with you, Chen and Zach. Our problem statement is that we're trying to create a deep learning pipeline that can identify whether a person is wearing a face mask correctly and also in real time. So it has to be relatively quick and small. In terms of the social impact side, obviously we've all been living through a pandemic for the last year, and we don't know if there will be future pandemics. So we have a couple of statistics here. One is from Nature saying that in just 2-3 months, wearing masks could have saved 100,000 lives just in the US. And then also another one here saying that population level compliance with mask wearing as well as contact tracing could have actually prevented the pandemic from growing. So if this helps prevent the current pandemic and also future pandemics, what are the issues that we have to tackle here? So one of them is, what if someone's wearing a mask incorrectly, or maybe they're wearing it correctly and then it changes position? And similarly, what if someone forgets to put their mask back on as they're walking? So there's a lot of potential uses here. For example, safeguarding public spaces and also allowing businesses to safely reopen.
Yeah, so we actually use two pipelines, and the first one is image classification. When we are given a set of images, we will first run them through a face detector, and then our mask classifier, and our output will be people marked with correctly wearing and no mask. In the dataset we are using are generated from the mask face net. There are 3 classes, each about 70,000 cases. And as you can see, people are wearing blue medical masks or incorrectly wearing them. We have tried 3 baseline models. The first one is a hair-based facial feature detector, which has about 70% accuracy. And then we tried random forest, and they all did pretty well, about 94 and 98% accuracy.
So when we were trying to decide what kind of advanced models to use for transfer learning, we consulted graphs like this one, and this was actually the main one. And you can see this plots accuracy versus operations and the size of bubbles as a number of parameters. So we picked from the top left. So DenseNet, MobileNet, Inception, and models like that. So you can see the models that we trained and tested here. They all achieved higher than 99% accuracy significantly, and the best performance was DenseNet, and the fastest model was ResNet. So we wanted to do some vanilla distillation to see if we could get the same accuracy faster. And so by training a CNN, we were able to achieve a pretty comparable accuracy at DenseNet while achieving very high inference speed with about 15% of the parameters that DenseNet has.
Okay, so this demo is run first through a multi-tag CNN for face detector, and then run through a ResNet that we use transfer learning for to detect the classification. As you can see, it does a pretty good job in classifying whether a mask is correctly worn, incorrectly worn, or not worn at all, and achieve around 7 frames per second for this video. So the next pipeline that we tried is a straight up object detection pipeline that has localization built in. So this pipeline would ideally combine the two components of the previous pipeline into a single neural network that can do both tasks really well. So for this data set, we need the bounding box of the faces with the mask or without a mask. So we scraped from 2 Kaggle data sets as well as the Coco data set, and then manually detecting faces to as the label. So the model that we decided to try is called YOLO, or short for You Only Look Once. So this model architecture models detection as a regression problem. So divides the image into a grid, and for each grid cell, it predicts the bounding box, the confidence score, as well as the class probability simultaneously, and then it fuses those output for the final detection. So this is our experiment result running the latest release, which is version 5 of YOLO. As you can see, it achieved around a 90% precision and about like 85% recall, which is pretty decent for this task. On the test data set, the mean average precision is around 90%. And this is a demo of YOLO V5 running on a just a YouTube video of someone walking across the Brooklyn Bridge. As you can see, it localizes the faces as it gets closer to the camera, and also detects two classes where they're wearing a mask correctly or not.
Yes, so here comes our conclusion. There is definitely a trade-off between the model speed and performance. The baselines are pretty quick, but the performance is a little bit compromised. So we need to consider this problem.
Another area for further research would be the diversity of our data set. Right now, we're using a synthetic data set that photoshops masks on top of people. But ideally, we want to explore other data sets with other masks and real masks.
And from the YOLO demo, we can see that we achieve a pretty good frame rate for real-world deployment and application for video data. And another extension we could possibly try is using tracking and history information to stabilize the detection results.